We continue our exploration of the network traffic data with a closer look at feature correlation and a few feature selection methods. First, we look at a heat map of the correlation matrix of the numeric features. We can see that there are a number of features that are moderately or strongly correlated with each other, suggesting possible redundant information. A number of features have a Pearson correlation coefficient of 0.7 or greater with another feature. We'll experiment with removing those features to improve model accuracy. Next, we're looking to see if any features vary together. By checking the covariance matrix heat map, we reveal that two features, STCPD and DTCPD, have a strong positive covariance. These features represent the source and destination TCP sequence numbers. These features may be providing similar information, and it may not be necessary to include both of these features in the final data set. Next, we calculate and plot the information gain of the numeric features and observe a few standouts. Among those exhibiting the highest information gain, we find S bytes, S load, and S mean. These features represent the number of bytes transmitted from the source, the number of bits per second, and mean packet size transmitted from the source to the destination. We also notice those providing the least information gain, which include those indicating whether the session was FTP, and if the source and destination use the same IP address and port numbers. Including the expanded categorical features reveals that most of those features provide very little or no information gain on the attack category, suggesting that the service, state, and protocol features may not be very useful. Note that the values on this graph are in logarithmic scale. For comparison, we next look at an analysis of variance F value of features calculated against the binarized attack category. We're looking for features with high variance, assuming those will provide more information. Again, this test includes only the original numeric features and not the expanded categories. We next check the F values for all of the expanded categorical features, and we see that many features have an F value near 10 to the first, while a few approach 10 to the fifth power. We'll check a few more techniques to identify useful features. First, we use a simple variance threshold method to select only those features with a high variance. In this case, the threshold is set to 0.8, the rationale being that these features with little or no variance will not provide much information. Another way we can measure the variance of the features is with the median absolute deviation. This statistic is similar to standard deviation, but more robust to outliers. Again, the assumption is that features with higher variability will provide more information. We can see a few features with a high median absolute deviation, but the majority very small or zero. Include with a selection of feature subsets for machine learning model experimentation. These features exhibit either high information gain or high variance. Also included are those which are not strongly correlated with each other.